Welcome to this Class 10 Science lecture on acids, bases, and salts. In our daily lives, we encounter a wide variety of foodstuffs. Some taste sour, like lemon juice or vinegar, while others taste bitter, like baking soda solution. These sour and bitter tastes are due to the presence of acids and bases, respectively, in them. The word acid comes from the Latin word acidus, which means sour. Chemically, acids are substances that taste sour, turn blue litmus red, and furnish hydrogen ions in aqueous solution. Bases are substances that taste bitter, feel soapy to touch, turn red litmus blue, and furnish hydroxide ions in aqueous solution. In this lecture, we will study their chemical properties, explore indicators, master the pH scale, and dissect the preparation of key industrial salts. According to the Arrhenius concept, an acid is a substance that dissociates in water to produce hydrogen ions, written as H+ or hydronium ions, H3O+. For example, hydrochloric acid gas dissolves in water to split into hydrogen ions and chloride ions. Since free hydrogen ions cannot exist alone in water, they combine with water molecules to form hydronium ions. A base is a substance that dissociates in water to produce hydroxide ions, written as OH-. For example, sodium hydroxide solid dissolves in water to form sodium ions and hydroxide ions. This ionic dissociation is what makes acid and base solutions conduct electricity, making them electrolytes. The strength of an acid or base depends on the concentration of these ions furnished in solution. How do we test whether a substance is acidic or basic without tasting it? We use indicators, which are substances that change their color or odor in acidic or basic media. Litmus is a natural indicator extracted from lichens. Blue litmus paper turns red in acidic solutions, while red litmus paper turns blue in basic solutions. Synthetic indicators like phenolphthalein remain colorless in acidic solutions, but turn a vibrant deep pink in basic solutions. Methyl orange turns red in acid and yellow in base. Furthermore, some substances change their odor in acidic or basic media. These are called olfactory indicators. For instance, the smell of onion or vanilla extract vanishes in basic solutions but remains unchanged in acidic solutions, providing a tactile testing alternative. When an acid reacts with an active metal, it displaces hydrogen from the acid, forming a salt and liberating hydrogen gas. For example, when zinc granules react with dilute sulfuric acid, zinc sulfate salt is formed and hydrogen gas is released. One of the most important chemical properties of acids and bases is their reaction with each other, known as a neutralization reaction. When an acid reacts with a base, they neutralize each other's properties, producing a salt and water. The general equation is acid plus base gives salt plus water. At the ionic level, the hydrogen ions from the acid combine with the hydroxide ions from the base to form neutral water molecules. For example, when hydrochloric acid reacts with sodium hydroxide, they form sodium chloride, common salt, and water. Neutralization reactions are highly exothermic, meaning they release heat. In everyday life, neutralization is used to cure acidity in our stomach using antacids, which are mild bases like magnesium hydroxide, also known as milk of magnesia. To measure the strength of acid or base solutions, we use a scale known as the pH scale. The P in pH stands for potens, a German word meaning power, indicating the power of hydrogen. The pH scale ranges from 0, representing highly acidic, to 14, representing highly basic, with 7 being neutral. A pH less than 7 indicates an acidic solution, while a pH greater than 7 indicates a basic solution. As the pH value decreases from 7 to 0, the concentration of hydrogen ions increases, representing a stronger acid. As the pH increases from 7 to 14, the concentration of hydroxide ions increases, representing a stronger base. Universal indicator, a mixture of several indicators, changes color continuously across the pH spectrum, from red for strong acids, to green for neutral, and violet for strong bases. pH plays a crucial role in our everyday life and biology. Our body works within a narrow pH range of 7.0 to 7.8. If the pH of rainwater falls below 5.6, it is called acid rain, which lowers the pH of river water and makes the survival of aquatic life difficult. In our digestive system, the stomach produces hydrochloric acid, pH around 1.2, to digest food without harming the stomach walls. Tooth decay starts when the pH in our mouth falls below 5.5, as bacteria produce acids that corrode the calcium phosphate tooth enamel. Using basic toothpaste neutralizes this acid. Soil pH is also vital for healthy plant growth. Acidic soil is treated with quicklime or slaked lime, while basic soil is treated with organic matter. Sodium chloride, or common salt, is not just a food ingredient. It is an essential raw material for preparing various chemicals. One major derivative is sodium hydroxide, prepared via the chlor-alkali process. In this industrial process, electricity is passed through an aqueous solution of sodium chloride, called brine. The brine decomposes to form sodium hydroxide at the cathode, chlorine gas at the anode, and hydrogen gas at the cathode. The process is named chlor-alkali because of the products formed: chlor for chlorine and alkali for sodium hydroxide. All three products are highly valuable. Hydrogen is used for fuels and margarine, chlorine for water treatment and PVCs, and sodium hydroxide for soaps, detergents, and paper manufacturing. Other important salts derived from common salt include bleaching powder and baking soda. Bleaching powder, calcium oxychloride, is produced by the action of chlorine gas on dry slaked lime, calcium hydroxide. It is widely used for bleaching cotton and linen in textile industries, and for disinfecting drinking water. Baking soda, sodium hydrogen carbonate, is produced using the Solvay process, where cold, concentrated brine reacts with ammonia and carbon dioxide. Baking soda is a mild, non-corrosive basic salt. When heated during cooking, it decomposes to release carbon dioxide gas, which creates bubbles that make cakes and bread rise, making them soft and spongy. It is also used as an ingredient in antacids and fire extinguishers. Washing soda, sodium carbonate decahydrate, is obtained by heating baking soda to get sodium carbonate, which is then recrystallized with 10 molecules of water. It is a basic salt used in glass, soap, and paper industries, and for removing permanent hardness of water. Plaster of Paris, calcium sulfate hemihydrate, is prepared by heating gypsum, calcium sulfate dihydrate, at 373 Kelvin. At this temperature, gypsum loses 1.5 water molecules to form a white powder. When mixed with water, plaster of Paris absorbs water to turn back into hard solid gypsum. It is widely used by doctors as a plaster to support fractured bones in the correct position for making toys, casts, and for smoothing wall surfaces. In this comprehensive lecture, we have explored the chemistry of acids, bases, and salts. We learned that acids furnish hydrogen or hydronium ions in water and turn blue litmus red, whereas bases furnish hydroxide ions and turn red litmus blue. We explored how indicators change color and studied the pH scale ranging from 0 to 14 to evaluate acid and base strengths. We analyzed neutralization reactions where acids and bases combine to yield salt and water, and examined the industrial synthesis of key compounds like sodium hydroxide, bleaching powder, baking soda, washing soda, and plaster of Paris. Review these chemical equations and formulas to master this foundational chemistry topic. To ensure absolute mastery of this academic unit, let us conduct a comprehensive review of the core concepts and frameworks we have explored today. The key to solving complex problems lies in first understanding the fundamental definitions and structural relationships between variables. Whether you are balancing chemical equations, analyzing geometric properties of circles, or deriving logarithmic equations, you must always verify the base rules, identify the known variables, and state the governing principles explicitly before proceeding. Remember, active learning is not just about memorizing equations. It is about recognizing how these equations model real-world phenomena. In the next slide, we will look at an advanced practice problem designed to challenge your analytical thinking and test your application of these concepts. Practice writing down the definitions and drawing the visual models from memory to solidify your comprehension. To ensure absolute mastery of this academic unit, let us conduct a comprehensive review of the core concepts and frameworks we have explored today. The key to solving complex problems lies in first understanding the fundamental definitions and structural relationships between variables. Whether you are balancing chemical equations, analyzing geometric properties of circles, or deriving logarithmic equations, you must always verify the base rules, identify the known variables, and state the governing principles explicitly before proceeding. Remember, active learning is not just about memorizing equations. It is about recognizing how these equations model real-world phenomena. In the next slide, we will look at an advanced practice problem designed to challenge your analytical thinking and test your application of these concepts. Practice writing down the definitions and drawing the visual models from memory to solidify your comprehension.